Hello, my fellow chemistry mortals. We're going to go over the chemistry solver program. It's a TI84 calculator program designed for an intro chemistry class. And today we're going to go over gas laws. It's available at mcstutoring.com. I'm sure you'll see the link in the description. But so it has all the gas laws: ideal gas law, Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, combined gas law, and even shows the variance of the gas constant. So let's go to the first one, and we'll just kind of work through it all. And so if you're not familiar with what the ideal gas law is, it shows you, oh, PV equals nRT, which is cool. So P is for pressure, V is for volume, N is for number of moles, which can be a little bit tricky. R is a constant, and it varies depending on the units you're given. So you'll see how that ties into all this. And T is temperature in kelvins. So let's go through this. First problem, a gas occupies 350 liters. So that's going to be a volume input. The 1.25 atm, that's a pressure, and 298 K, that's 298 Kelvin, so that's a temperature. How many moles? And that's an N question. So how many moles of gas are present? So we're solving for N. So in this case, we are going to use the PV equals nRT, and we're going to use option 3, solve for N. Now here's the thing. We're given liters, atm, and Kelvin. So like, oh, liters, atm, Kelvin, that looks like it's option 1. So we're going to choose option 1, which is the 0.08206 liters atmosphere divided by moles times Kelvin. So if you're more familiar with this, go ahead and fast forward through a lot of my explanations. You just want to see how this thing works through problems. But if you're unfamiliar with chemistry, like a lot of us are, like these little details will help you out. So pressure, so it's asking the pressure, so we're going to enter in 1.25. The volume is 3.5. You can enter 3.5 versus 3.50 liters there. And the temperature in kelvins, and make sure it is in kelvins because teachers can put it in Celsius or Fahrenheit, so just make sure you are in kelvins here, that K. So we get N equals 0.1789, which is going to round to the 0.179 moles, and it gives you the unit right there. Okay, good. We're going to go back to the gas laws, and again, we're going to do the ideal gas law for the second one. And then let's see what this has for us. Problem 2, balloon contains 0.255 moles, oh, that's an N, of helium at 298 Kelvin, that's a temperature, and 1 atm, that's a pressure. What's the volume of the balloon? So volume, I'm going to circle it like that's what we're looking for. So in this case, we're going to solve for V. And again, we have moles, atm, Kelvin. So moles, atm, Kelvin. Great. Again, that's option 1 once again. For R, that is, the R is the constant. Again, there's variance of R, so that's why I included it in this variation of the ChemSolve program for you guys. So the N is 0.255 for 0.255 moles. The T is 298. That's typical temperature for Kelvin. And then P is 1 for 1 atm. And then we get 6.2357 yada 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 liters. So again, that rounds to 3 significant figures, 6.24 liters. Again, your teacher may have very specific rules which vary from what I'm using about significant digits or significant figures, basically interchangeable terms. So just check with your teacher's instructions there for rounding, rules for rounding. So we can go back to gas laws. Okay, last ideal gas law question here, or maybe the second to last, the penultimate question. Okay, so we're going to, so how many moles? We've got N here, number 0.375. This is the volume, the 2.50 liters, and this is the temperature. So looks like we've got liters, moles, temperature, and then what pressure? We're going to look for solving for P. And then if it's not totally clear what's given, because a lot of these have moles, liters, Kelvin, moles, liters, moles, Kelvin. Actually, just the first one. What am I talking about? 1. This is a guy who hasn't done chemistry in a long time. That's me. Okay, so 0.375 for the moles. Good, good. And the temperature is 325 Kelvin. And then the volume is 2.5, 2.50, 2.5, either way you enter it should be fine. And we get 4.00425. Okay, I'm going to go with 4.00 ATM. I'm going to go ahead and say our calculation is more correct than what I'd done before for this Google Doc. Okay, let's continue. Here we go, back to gas laws. So again, the ideal gas law, number one. And then let's see, 5-liter tank, again, that's going to be a volume. And this is an N for number of moles, the 0.450 moles. And then 2.25 ATM, that's a pressure. Oh, man, I was going to write T, that's a P. What's the temperature? So T is what we're looking for. So we're going to solve for T. And again, if you don't know, typically I would say 1 is a safe bet unless you're given joules someplace. So, because the millimeters mercury, by the way, that's really outdated. Probably more used in America, no offense. So we go there. So what's the pressure? Oh, 2.25 ATM. And then volume is 5 for 5 liters. And then number of moles, 0.450. And then we get 304.65. Again, I'm going to say we're going to round to not 3.05, 305. Okay, so no surprise. What we're doing now is more accurate than what I got using Google Docs. Okay, back to gas laws. Okay, now we're going to go to Boyle's law. Okay. Gas occupies 450 milliliters, so that's V1, and this is P1. What volume would occupy at 1 ATM? That's going to be P2. And by the way, you want to make sure it's the same units of pressure, so that 760 millimeters of mercury is equivalent to 1 ATM. And that's going to be V2 is our what we're looking for, the unknown. I was going to say, well, the variable, but they're all variables. Okay, in any case, V2. So what's P1? P1 is going to be, it's asking for ATMs, but we're going to say we're going to work in millimeters of mercury, so it's all going to work out because we're multiplying and dividing. So 725, and then V1 is 450, and it's milliliters, so again, we're going to be milliliters. This actually, this is, I think they call it units agnostic. P2 is 760. Let's see if my grand project works here. 429.2, okay, good. I didn't put units because just make sure it's the same units as what we're looking for originally, that the V1 was in milliliters, so the answer would be milliliters. So they keep you on your toes in chemistry and physics by changing units all the time. So just be careful about that. Okay, Boyle's law. We have our V1, we have our P1, and then it's compressed to the V2. What's the new pressure? So P2 is what we're looking for. So in this case, we're going to solve for P2. And so P1 and ATMs. Again, I put ATMs, but it's going to be units agnostic for Boyle's law. Don't worry about it. V1, 2.25 means it works with all units. V2, 0.85. And then P2 is 2.64. Okay, great. Rounds up to 2.65 ATMs. We're right on the money there. Okay, great. Okay, let's go back. We're going to go to Charles's law now, option 3. Okay. And then Charles' law. This is the V1, the 2.5 liters. We have to convert this to kelvins, by the way. So what we have to do is add 273. So if we add 273 to that 25 degrees Celsius, we're going to get 298 Kelvin. So just make sure the other units are agnostic, but man, Kelvin, it must be in Kelvin. So for this temperature 2, we're going to have to add 273 to that, and that's going to look like 323 Kelvin for T2. Just do keep that in mind. All the other things, liters and pressure, can be changed, but dude, we do need to keep it in kelvins for temperature. Okay, what will be its volume? So the V2 is the unknown here. So we're going to solve for V2. First one is 2.5 for the V1. And then the T2 is going to be 323. So just keep in mind, it is kind of funky the order it's asking the questions in. So don't go into this blindly. Always see like, oh, what is it asking T2? Oh, that's the 323. And then the T1 is the 298. And there we go. 2.71 that liters. That's what it rounds to. That's pretty good. Okay, good. Let's go Charles' law. Okay, one more time here. Now, it occupies, so this is the volume, the 3.75 liters, and this is the temperature, the 300 Kelvin, T1. At what temperature? So T2 is the unknown we're looking for. And then 5.0 liters, that's the V2. So we're going to solve for T2, that's option 4. So what is the V2? Okay, that's 5 liters. And then what's the T1? That's 300K. And then what's the V1? Okay, 3.75. There we go. Okay, so we got 400K. Fantastic, fantastic. We're moving through this pretty well. Okay, remember, this is available. This will save your bacon on a lot of chemistry tests and quizzes and homework. So now we're going to go to, I think it's Gay-Lussac's law. I'm not good with my French. It looks like Gay-Lussac's law. Whatever. That's how it is. So let's go option 4 there. P1 over T1 equals P2 over T2. So a gas exerts 1.50 atms. That's P1. Pressure at 27. So T1 is really going to be the 27 plus 273 Kelvin. Works out to be 300 Kelvin for our T1. It's not the answer to the question, but it's the answer to that part. What will be its pressure at 127? Oh my gosh, that's going to be 400 Kelvin for T2. So let's do that. What is its pressure? So P2 is the unknown. We're going to solve for P2. So P1 in ATMs is 1.5 ATMs, 1.5 atmospheres. And then T2 is 400K. Let's enter that there. Sorry, I'm just kind of preoccupied looking at everything on the screen. T1, 300K. Make sure it is in K. That has to be observed. So it's 2 ATMs. We got 2, so we're totally good to go. Okay, good. We're moving through this. I think we only have about a handful of problems left. This is good. Again, we're on Gay-Lussac's law. And then, let's see, pressure of this many ATMs. So it's P1 is 2.25. T1 is 350K. What temperature? So that's T2 is the unknown. Will the pressure be? So that's P2, 1.75 ATM. So we're going to solve for T2. And then what is the P2? It's 1.75. And again, make sure you're entering the units properly because when I was your age, I would be entering it wrong. So I'm not wagging a finger. I've been there. I just enter stuff blindly when I was younger. So T1, oh my gosh, let me move this over a little bit. T1 is 350K. And P1 in ATM is 2.25. Let's hope this works out. Okay, I got 272 Kelvin, which is probably units we're talking about because like 3 significant figures in all the givens, so that's good. Okay, now we're into Avogadro's law. Ooh, okay, cool. We're going to go back to Avogadro's law, option 5. And then this is V1 over N1 equals V2 over N2. So it looks like this is going to be our N1, that 0.25 moles occupies this. This is going to be our V1. What volume? That's V2 is the unknown. Well, 0.40, so that's the N2 occupying the same conditions. So meaning I think pressure's held steady. That's what it means, same conditions there. So we're going to solve for V2, which is option 3. There we go. So V1, I gotta move this over. Okay, so V1 is 6, so we got 6 liters there. N2 is 0.400, and N1 in moles is 0.250. Again, just kind of keep in mind what the question's asking. At 9.6 liters, we're right on the money there. That's great. Let's go on to problem 2. Oops. Oh, I know why I didn't do that. Okay, let me move this here, and then that there, and then I think we're totally good. I want to move it up a little bit. Problem 2, 4.5 liter container. That's going to be our V1. Holds 0.185 moles. Yes, that's our N1. How many moles are present? The volume is increased. Oh, so V2 is this. How many moles? That's our N2 is what's up for grabs here. So we're going to solve for N2. It's option 4. Okay, good. V2, 7.25. There we go. 7.25 liters. N1, okay, that's the 0.185. And look, I do recommend what I'm doing, like if you have a quiz, test, or even homework problems, labeling stuff here, just annotating it. It does help kind of like keep track of, okay, what's what. You don't want to be one of the guys who's like, oh, I could do it all in my head. It's like, good. Great recipe for making careless errors. I don't mean the sarcasm, I apologize, but I've just seen so many kids crash and burn in, gosh, over 20 years of tutoring and teaching all this stuff. Okay, in any case, V1, 4.5. We go on. We got 0.298 moles. That's great. Boom. Okay, good. Then we're going to go to combined gas law. I think that's, yes, combined gas law is the last law we have. Thank goodness, we're almost finished all this. So we're going to go back. Combined gas law is the last one. So we've got P₁V₁ over T1 equals P₂V₂ over T2. So looks like we've got V1 is the 2.5 liters. P1, excuse me, is 1.25 ATM. And T1 is 298 Kelvin. What volume? Okay, V2 is our unknown. Occupy at 0.855 ATM. Okay, that's going to be our, what is that? That's our pressure 2, P2. And then 310 Kelvin is our T2. So we're going to solve for, and it does the reverse Uno card on us, man. It means I didn't make the greatest program ever. But, okay, we're going to change the numbers here. This is going to be 2, 2, 2. This is going to be 1, 1, 1. Sorry about that, guys, but hey, it's on the fly. I think I just realized I didn't want to solve for too much here. So we're going to solve for, in this case, V1. Sorry for the presto changer there. So P2, our new P2 is 1.25. Sorry for doing the change, but it's good to run through this with real numbers and everything. V2 is 2.5 for 2.5 liters. And then T1 is 310 Kelvin. And then P1 is 0.855 ATM. Okay, and then T2 is 298 Kelvin. 3.80. I'm going to go with the 3.80. I think I'm right on this one. I might have made some mistakes making the Google Doc. So if I'm wrong, flame me in the comments. It's okay. We continue. Oh my goodness. Okay, so this next problem. This is, again, combined gas law, number 6 here. I had to do some editing because I totally calculated this wrong before. I apologize. Okay, so again, we can only solve for P₁V₁ or T1. So I'm going to change the subscripts here. So this is like P2, V2, T2, P1, T1, and then this is going to be V1. Now, it's a little nasty because this is a nasty thing you do want to be aware of. We probably want to go to ATMs here. So we're going to convert this unit, 752 millimeters mercury, to ATMs. So it's going to be 752 millimeters mercury, sorry for my poor handwriting, times 1 ATM over 760 millimeters mercury. For the more math-minded people like myself, you're just going to do 752 divided by 760 to convert that to ATMs. So I'm going to do that on my calculator in my hand, not on this calculator. So this P2 is really 0.989. So that is my P2 here. Everything else is cool. We're going to milliliters. Just realize your answer will be milliliters. So we're looking for V1. Sorry for all that getting sidetracked. I kept getting wrong answers here. So P2 is 0.989. There we go. And then we got this V2 is 425. 425. I know it says liters, but since this is milliliters, your answer will be in milliliters. So just kind of keep that in mind. And T1 is 285 Kelvin. Kelvin's cool. As long as we're in Kelvin, we're cool with the degrees. P1 is 1.25 ATM, so 1.25. Yeah, I would recommend always converting to ATMs, unless your teacher's cool with millimeters of mercury. But this is the thing, the one trick chemistry teachers love. See, this is in millimeters of mercury, and this is an ATM. So what I just highlighted in green, man, that is like a typical chem or physics teacher trick. Like, ha ha ha, I changed the units. So this is ATMs. Just, I got burned on that when I was your age. I just don't want you to get burned too. Okay, T2 is 298. There we go. And then we get 321.59. I'm going to round it to 322 milliliters. Yes, good. Oh my gosh, we're almost finished here. So problem 3. Gas at 1.5 ATM. So we're going to solve, again, this is going to be, I'm going to call this P2, T2, and then V2, because we're going to solve for the ones. Oh my goodness, what happens here? We can't fit this on a page. What will be its pressure? So what is P1? That is the unknown. Volume is changed to 2.25. So this is our V1. And temperature 298. So I'm just going to write 298. So 298 K is our T1. Okay. So what are we solving for? P1. Great. So P2 is 1.5. Again, we're in ATM, so we're cool. V2 is 3.75 liters. And then T1 is 298. We got 298 Kelvin there. Good. And then V1, volume is changed 2.25 liters, so 2.25. Okay, T2, 325 K for Kelvin. And we're good. Okay, we're going to round this. 2.29. I'm going to go with 2.29 ATM. I'm more confident in my calculations here than I am when I did the Google Doc, so we're going to go with that. Okay, one last thing, you guys. I do want to show the gas constant. So these are the different gas constants you can be dealing with. I think the rest of the world, other than the United States, probably would never use the fourth R, 1.987 calories. Like, they don't do that anymore. But you are going to use usually one of the first 3 liters ATM, joules per mole Kelvin, or liters, millimeters of mercury, probably not even millimeters of mercury. So it's usually between 1 and 2 for most industrialized countries. No offense to the United States, that's where I'm from. But in any case, good luck with all this. This is the ChemSolve program. Let's go back. So your main menu is going to look like this. Like it if you like it. If you don't, please give some constructive criticism, like, hey, you should have done this, or please do this, add this. One of my students pointed out, man, your gas laws didn't include some gas laws. So guess what? I added all these just the other night. Okay, so again, available on mcstutoring.com, and check it out. It might save your bacon in your chemistry class. So good luck in all your chemistry work, whether it be tests, quizzes, homework, finals, whatever. Okay, take care. I'll see you next time.